So we're trying a little bit of a different format with the video workshop series. So the first two presentations that we had this semester were pure research-based presentations. And then this presentation is going to be more of kind of an overview of facial recognition technology and talking about how you can use it for your own research. After this presentation, in a couple of weeks, we will send out an email to participants to try to get an assessment of which format they preferred and whether or not we needed to alter things, alter the workshop series moving forward. So interested to hear your feedback as we improve on what we were providing you over the next couple of years. So the motivation for the facial recognition discussion is that Oliver Rittman gave a very nice talk that we will eventually have up on the CCSE, the Center for C-SPAN Scholarship and Engagement's website by the end of the semester. And in Oliver's talk, he used facial recognition technology to identify members of Congress, the extent to which they were attentive during legislative debates. And so this is supposed to provide a little bit of an overview of the sorts of techniques that he used in that paper, and then also to try to give you the sense of sort of the discussion within this literature about facial recognition and its potential utility. So to start with, I just want to talk about the academic research that it is in this area. So Patrick Stewart is in the chat. So Patrick and Eric Busey are probably the two people who've done the most in terms of facial recognition in political science. So in this paper, there's manual coding of faces. I'm not necessarily going to go into that. I'm going to talk more about automated methods, and I'm going to circle back to this paper. The other trend in political science is that there's a couple of papers. So this is a JOP article in which facial recognition technology is the independent variable, and the dependent variable is things like voter turnout. And so those are the use cases that we currently see. But as we'll find out, there's a lot of other ways that facial recognition technology can be used for academic research, and I hope to elucidate some of those throughout the talk. So facial recognition is the problem of identifying and verifying people in photographs using their face, and it generally comes in two flavors. So one is face verification, where you're trying to confirm whether or not two people are the same faces. And then there's a face identification, which is assigning a name to a given face. So face verification would be what you would do on your iPhone, for example, to unlock your phone. Facial identification would be, is this person Donald Trump, or is this person a member of Congress? So the main difference between these two approaches is a one-to-one, which is what facial verification is, versus a one-to-many approach. Generally speaking, one-to-one approach from a technical standpoint is much easier than a one-to-many, because in a one-to-one approach, you essentially know what the random chance is, because there's a 50-50 chance that this, when you ask a computer, are these two photos the same? If it's flipping a coin, it'll be right about 50% of the time, which has a good way for us to know whether or not the technology is being effective. So generally speaking, facial recognition involves 4 steps. Face detection, which is locating a box face in an image and marking it with a bounding box. I'll show examples of that here in a second. Face alignment, which is normalizing the face to be consistent with training data. As we'll find out, one of the challenges with facial recognition is that the data sets that we use to train facial recognition models are not necessarily the faces that we see in the quote unquote real world. And so the face alignment step is a normalization step to make the faces that we see in the quote unquote real world line up with the training data that we're used to building the algorithm. Feature extraction is extracting features from the face that can be used for the facial recognition task. And then finally, face matching is performing matching on the face against some sort of training data, be it facial expressions, which we'll talk about here, or also just facial identification tasks, like whether or not this picture is Donald Trump or a member of Congress. So let's first talk about face detection before we get into some of the work that I've done in this area, which will be towards the latter half of the talk. So facial detection is also not a trivial task. So it's essentially a specific form of object recognition. So there's a large literature about object recognition and computer vision. So this would be something like, here's an image, label all the things in the image, and the algorithm would say, this is a bike, this is a cat, this is a dog, this is a person. Face detection is the same thing, except it's looking for a very specific type of object, i.e. the human face, which has specific properties that have been hashed out for several decades within the computer vision literature. So just as there can be multiple stop signs, which makes object detection challenging, there's a high degree of variability when it comes to the human face, which means facial recognition on itself is a very challenging object recognition problem, and it's compounded by a variety of factors. So the orientation of a face, so whether or not somebody's looking straight at the camera versus a profile shot. Lighting differences, so is it dark, is it light? So in terms of things like facial identification, that could matter if you have a dark scene versus a light scene. Glasses, so whether or not somebody appears like this or that, also can affect the effectiveness of facial recognition. Post COVID-19, whether or not an individual is wearing a mask, there's a lot of work in this area as well. Facial hair, so did the person shave between image 1 and image 2? Does that make this individual the same? And then finally, ages. We know that over the duration of somebody's life, their face changes quite a bit. And we want to have an algorithm that can identify those people over time, which again is very, very challenging. So there's a lot of APIs that are available. And so the way that I will distribute some of these examples is that instead of walking through a lot of these in the slides today, if you'd like me to send these examples to you directly, you can send me an email. I'll include them at the end. But I also post these with the actual video that's associated with this talk once we get it up onto the website. So, so the bounding boxes, so these green boxes around my face, this is what we're talking about in terms of face detection and saying that this is a face. Of course, this seems like a trivial problem, but if you have like, for example, you can see in the background here, there's like a photo with some people in it. Sometimes it can misidentify photos of faces versus an actual face, which can cause problems for whatever it is that you're trying to do. But the key to remember about facial recognition is that this is the first task. So if the computer gets this wrong, then everything down the pipe will also be wrong, which is an important point and why it's a particularly challenging problem. So now, once we have somebody's face, when you use an API, an automated programming interface like Google Vision or Microsoft Azure, when you use those APIs, the image that you're giving it, there's an alignment step that's happening behind the scenes that you're not going to be fully aware of. So when I talk about face alignment, all of that is happening in this software, and it's not necessarily apparent to the user, but it's all happening in the background. So let's talk about face alignment, which is the second step in the facial recognition task. So facial alignment is a computer vision technology to evaluate the geometric structure of a human face within digital images. So there's multiple face alignment algorithms. So there's two-dimensional alignment, three-dimensional alignment, but they all have the same sort of idea, which is to take a bounding box. So once you've drawn a bounding box around a human face, rotate it and tilt it in a particular way so it lines up with the images that you're using to train the algorithm. This is a really important step because if there's a misalignment, you can have errors in terms of facial detection or whatever it is that you're trying to use the algorithm for. So the main challenges for face alignment arises from low-level image ambiguities, and it's very similar to the problems that we just discussed with respect to facial detection. So reflections in the images. So you can see in my computer now, I have reflections in my glasses. That could affect the ability of the face alignment algorithm to properly or orient my face to match with training data. Occlusion, so whether or not my face is hidden, could also affect this with things like hats or whatever. Background clutter, so if you have too much happening behind you, that could affect a face alignment algorithm, because one of the challenges that's happening with facial recognition is that once there's a bounding box or a box drawn around a given face, what it's trying to do is also detect the edges of that face. So they're trying to figure out what sections of that face is the face versus the background. And so if there's a lot of clutter in the background, that makes that identifying the edges of that face even more difficult, which again makes it harder to do the alignment step that is necessary for most facial recognition tasks. And then different facial features and textures could also make this problematic. So in order to address these issues, face alignment algorithms impose very explicit structure onto the human face. And so these face models use prior knowledge about the human face and then collect image evidence of facial features that match those prior knowledge of the human face, and then fusing those priors with those observations in order to properly align the face in the image. So this is obviously very technical, but one of the challenges, and it's not just a challenge, but one of the ways that bias can be introduced into facial recognition is by the strong assumptions that previous face models made about the way the human face was structured. So there's certain ratios with respect to the length and width of a human face. If you don't meet these kind of golden ratios, face alignment could be problematic. There's a lot of other things that were made in these early face models that didn't necessarily port to all versions of human faces, which made facial recognition challenging early on. So here's an example that I grabbed from a paper that I assigned my class regarding facial alignment. And this is exactly what it's doing. So there's a bounding box in panel A. In panel B, it's identifying a tilt to the eyes in the original image. Panel C, it zooms into the face, and then it orients the eyes so they're essentially parallel to the ground. That face alignment step is important because if all the training data is oriented similar to panel C, then there could be a misidentification in terms of the original image in panel A if that alignment step does not occur. So the next step is feature extraction. So feature extraction is also an important part of the process. It also includes a very strict model of what the human face entails. So feature extraction is just like any other problem in computer vision in the sense that we want to spend time extracting features that are necessary for whatever task that we have at hand, but we don't want to extract too many things because that starts to become computationally intensive. And so as these algorithms have developed over time, the question is which portions of the human face are most important for facial recognition tasks, be it verification or identification. So ultimately, this is a dimension reductionality problem, which is something that happens in all machine learning, not just computer vision, in which you're trying to reduce the dimensionality of our data in such a way to make it useful for classification purposes, but not overbearing. So the general problems in this step can be summarized within 3 questions. So the first is, are we going to use holistic features or are we going to use analytic or subparts of the human face? So when we do the facial extraction, feature extraction, do we care about the whole face or do we care about specific segments of the face, i.e. the eyes, mouth, etc.? When I mean the whole face, it means that should we just take a bounding box around the face and just say that is the face, and then use that for a classification test, ignoring things like identifying the nose or identifying the mouth or identifying the eyes? That's an important question that has to be asked when you formulate these types of algorithms. The second is temporal information going to be used? So do we care about the face in motion or the face changing over time? Can also be important. And then finally, do you want to use a 2D or 3D representation of the human face when extracting these features? So generally speaking, the features that we extract from this step in the process can either be geometric, so it can either be the shape and the location of specific facial components, again, like the eyes, the mouth, the nose, so forth and so on, or it can be appearance features such as wrinkles or furrows, or what you get in the Google Vision API is these little dots that are identifying the contours of the eyebrows that I have, as well as my eyes, but the boundaries of my nose, my cheekbone, and then here are my lips, and then the boundaries of my chin. So are these the only features that we need for the recognition task? Maybe yes, maybe no. But generally speaking, these are the ones that have been converged on in the literature for the purposes of these types of models. So at this point, it should be pretty, you should have a basic understanding of just kind of the steps of a facial recognition algorithm. And now I want to slow down a bit and just talk about some of the applications of facial recognition technology within the social sciences, which is what I'm mostly familiar with. So the first thing I'll talk about is Patrick Stewart and Eric Busey's work. Again, I referenced this at the beginning. These folks have done a lot of work with respect to facial recognition. And so their work is definitely a good place to start in terms of what I would use this type of model for in terms of social science inference. So generally speaking, these papers, and when I say papers, there is extensive literature that Patrick Stewart and Eric Busey have produced on these topics. Generally speaking, deals with facial expression recognition. So this is not trying to say, is this image Donald Trump or is this image Joe Biden? Instead, it's trying to say, is this person happy? Is this person sad? Does this person have a positive affect, a negative affect? And these come in a lot of different shapes and sizes. So one application of facial expression technology is what is called affective computing. So you don't see this as much in the last couple of years, but it used to be a hot topic 5 to 10 years ago. And so this was all about human computer interfaces. So I would say the extent to which that we have affective computing in our everyday lives would be something like a personal assistant, an Amazon Alexa, for example, which could maybe understand kind of the tenor of your voice and maybe have a different reaction to your voice depending on how you're interacting with it. So that's what affective computing is about, which is sensing, detecting, and interpreting human affective states, human emotions, and defining means for handling them in some sort of automated fashion. Another application of facial expression recognition is deception. So there's lots of studies in psychology that talk about visual features of the human face that are associated with deception. And so perhaps we would want to develop a facial expression recognition system that tries to detect deception in a number of different settings. Attitude. So there's research in psychology that has found that facial mimicry, so the extent to which people mimic each other's faces, is oftentimes an unconscious gesture of wanting to get along with somebody. So it's a way to determine whether or not there's a strong social cohesion or bond. And then finally, aggression. So identifying friendly or unfriendly faces to prevent or encourage interpersonal encounters is something that is also used within this literature. So before I give you examples of what spatial expression recognition look like in practice, I want to pause for a second and just say that with respect to this type of technology, there's a larger amount of pause, especially in companies like Google and Microsoft, about whether or not this type of technology is actually ethical. It's not necessarily ethical, but whether or not it's a useful tool to provide to users. And so the main issue with these types of approaches is that you're trying to infer somebody's subconscious state. And if that subconscious state, especially if you think about something like deception, is something that that individual is trying to hide, is that something that that individual could actually consent to as a research participant? And is that something that we should actually be doing, trying to kind of read between the lines with respect to somebody's response? So I think there's a lot of good research reasons why we'd want to do this, but this is why a lot of these features are being removed from the Google Vision API, for example, in a couple of months, because there is a little bit of concern about whether or not these tools are good writ large for the public. And that would certainly be something that I'd want to engage with in the Q&A. So a lot of things can hinder facial expression recognition. So face image resolution. So do you have high res image, low res image? Higher resolution images, the better in terms of both facial expression recognition as well as facial recognition writ large. Face image quality. So is it blurred, out of focus, low or high contrast could all implicate the effectiveness of these algorithms. Head orientation again. So are they looking to the side? Are they looking straight on? Facial expression. So unless a person is quiet and motionless, this could certainly affect it as well. Lighting conditions, so facial images can be seen within different illumination patterns, which we've already talked about. Eyeglasses, clothes, other things that could occlude the image could also implicate it. And then again, aging, a person's faces change over time, so we'd want to develop a system that is robust to those things. So to provide you an example of what this would look like in practice, I did some images of myself prior to this talk earlier this morning and saw how the Google Vision API did in assessing these things. So this first image, I would say, is neutral. So it's just me sitting in front of my computer. And you can see in terms of the emotions that they're trying to articulate or identify: joy, sorrow, anger, surprise, those four things, relatively low, which is what we would ultimately expect. Now, I did my happy face. So I did a big smile in front of the camera. And I think this is an area where the Google Vision API, both in this example and also in my own practice, tends to do fairly well, is in terms of smile identification, which is ultimately captured in this joy metric in the API. It does a pretty good job at identifying that particular facial feature. The second facial feature that it does really well on the surprise look. So this is the overly surprised version of myself. And you can see that it does a really good job at identifying that particular facial expression. Now, what's key about this, and again, it comes back to facial expression recognition, is this actual surprise? So I can tell you at this point, I'm not surprised when I'm taking this image because I'm just producing an example for this exercise. And so that's really where it comes down to, is that we can say that the image seems like somebody's surprised, but there's definitely a question about whether or not they are actually surprised, which oftentimes we're never going to be able to know. Doesn't necessarily mean that it can't be used for research purposes, but it's certainly something that we should keep in mind as this technology becomes more utilized. So in terms of the sorrow metric, I found a lot of inconsistencies. So this was my first crack at producing a sad face or a sorrow face, and you can see it didn't really move any of the metrics in this end. Then I tried to get really sad, and that seemed to also not do anything. And so I don't know exactly the type of facial expression that triggers the sorrow label in the Google Vision API, but it doesn't seem to be either of these expressions. So anger, this was the overly angry face that I produced. So clenched fists, really, really angry teeth. And you can see that it does trigger a little bit in terms of anger possibility. But on the top metric, you can see that it also thinks of it as being maybe not necessarily joy in this instance, but when I create a less version of the this angry motif, it seems like it's mislabeling it as joy. So all of this is to say that when it comes to facial expression tasks, I think there's definitely some things that these algorithms can do well at. One is smile detection, which is here. Smile detection has been something that the computer vision literature has been working on for a very long time. And it has specific facial properties that are very easy to implement in an algorithmic fashion. Because, again, if you think about, if you don't mind, I'm going to go back. If you think about the type of information that the algorithm is obtaining from the human face, you can see how a smile is something that could be very easily identified when you're already trying to identify the corners of the mouth, et cetera, when identifying these tasks. So, so returning to the Stewart and Busey work, one thing that's important to note about these papers is that this is perhaps the reason why they use human coders in a lot of this literature and don't necessarily rely exclusively on automated approaches. I know Eric Busey has a couple of papers where it looks at kind of more automated facial recognition tasks, but it's much more it's harder than having humans code. Now, certainly things related to whether or not it's expressed emotion versus felt emotion, those arguments could certainly be levied in these instances as well. But this is oftentimes why a lot of this literature relies on human coding. So when we talk about facial expression recognition, it doesn't necessarily have to exclusively be facial expression recognition in terms of automated computer vision. So facial recognition, again, this idea of face verification, which is one-to-one mapping, or face identification, this is where I've spent most of my efforts in terms of this type of technology, is thinking about how we can improve facial recognition tasks. And so specifically, oftentimes in video footage, especially, so on a channel like C-SPAN, for example, we may want to know who is speaking at a given time. And oftentimes the human face is a good way to identify and differentiate between one speaker versus another. Indeed, text-based differentiation or diarization between speakers is almost impossible. And then audio diarization, or splitting up speakers using audio signals, also incredibly challenging, especially in comparison to using the human face to differentiate between two speakers. So again, for me, a lot of this is based on just practicality of, I want to identify who is speaking during a given speech. And I know some of the folks who are attending today have already contacted me, and this is often the problem that they have, is they're trying to identify, is this person the same person as this person, or tell me who this is. So here's an image, query this databases of faces, tell me which one of these faces is that person, is another thing that these individuals, that this task ultimately tries to get at. So to provide a little more sense of the problem, And the reason why facial verification, which is what I'm showing you over here, where you have two images, is a much easier problem than facial identification, where you're taking a single image and trying to query a database of 100 people, 1,000 people, 1,000,000 people. Much, much harder problem, because in a facial verification task, all you're asking is, are these two images the same person, or are these two images the same? In a facial identification system, you're trying to say, here is an image, look through this haystack and tell me where else you see this image. That is a much harder problem. And consequently, systems that are based on facial identification tend to have a higher fail rate than systems based on facial verification. So facial recognition itself, so there has been some concern about facial expression recognition in the tech industry. Specifically, Zoom announced that it had a program in which they were going to allow people to buy, essentially assess things like the emotionality of participants within the Zoom setting. And then they ultimately scrapped that whole program because of these concerns about things like consent, et cetera, which made it hard for them to move forward. At least they thought it would be difficult for them to move forward in a profitable manner. But facial recognition issues in the popular press have mostly dealt with facial identification, i.e., let's have a body camera, let's put facial recognition into the body camera. The body camera is filming the outside world, and it's watching footage, and then ultimately it's querying that footage with some sort of mugshot database, and then we're going to say that's a criminal, that's somebody who needs to be stopped. That type of facial recognition problem is really, really challenging, and many would say impossible, which is why Axon, which is the largest manufacturer of body cameras in the United States, has ultimately removed facial recognition technology from its platform. And so this paragraph does a nice job of summarizing one of the problems that we face when assessing facial recognition in the quote unquote real world. So the TLDR of this paragraph is twofold. So the first is that facial recognition accuracy measures are mostly compared to these gold standard databases, which are oftentimes people looking straight at the camera, oftentimes are high resolution images, which is not necessarily the type of data that something like facial recognition and body cameras ultimately faces. So in that type of data set, often called in the wild images, facial recognition performance, i.e. identifying a criminal or something like that, has been shown to prove largely ineffective, or at least has a much lower success rate than the kind of these gold standards. The second is all of these questions about the camera moving, whether or not the individual is far away, the lighting conditions, et cetera. All of these things are relevant to facial recognition in this setting as well, and all hinder performance. But the third thing that I would say about Axon's position is that success in this format is really difficult to say. So is the success is the success trying to be garnered in terms of the number of false positives? So i.e. the number of times my algorithm says that somebody is a criminal, for example, and in reality that they're not? Or is it based purely on the overall accuracy of the algorithm? And that's a really hard problem for companies like Axon and others to answer, which is ultimately why they scrapped this particular technology. Within facial recognition too, there's a lot of concern, also echoed by Axon and others, in terms of algorithmic bias. And so algorithmic bias has been covered in a lot of different settings. So generally speaking, it's systematic and repeatable errors in a computer system that create unfair outcomes, such as privileging one arbitrary group over another. Also occurs when an algorithm produces results that are systematically prejudiced due to erroneous assumptions in the machine learning process. So there's generally four types of algorithmic bias that I just want to quickly go over, and then I'm going to focus on the algorithmic bias that specifically makes facial recognition technology increasingly difficult to utilize in a lot of settings. So the first is interaction bias. So the algorithm learns by interacting with users, which can introduce bias. So this would be somebody develops an algorithm that as it interacts with people on like a social media platform, for example, it learns from those individuals and then starts to reflect the biases that those individuals have within the platform. Emergent bias, an algorithm only gives us information that confirms our pre-existing biases. So emergent bias is a echo chamber on social media, for example, in which you only encounter individuals who agree with yourself. Latent bias, an algorithm may incorrectly identify something based on historical data or because of a stereotype that exists in society. And then selection bias, the data set that's used to train an algorithm, overrepresents one certain group and underrepresents another. So if you want a discussion of all of these types of biases, John Oliver, so this is actually on YouTube, a couple of weeks ago had a whole episode on artificial intelligence where he does a very good job of talking about each of these types of biases and provides examples of them. And so that's definitely a good resource. When it comes to facial recognition, the two things that we're most concerned about is latent and selection bias. And latent bias in facial recognition would be something like because in the past these facial features have been effective at predicting certain things within the facial recognition world, we're going to rely on those. And so certainly latent bias implicates facial recognition technology, but honestly I think selection bias is probably the thing that we're most concerned about, which is that the data set that we use to train facial recognition technologies is overrepresents one certain group over another. And so the best example of selection bias I actually found when I was putting together the slides for today's presentation. And so there's an encyclopedia of biometrics, which is actually a really good resource for providing good overviews of a lot of the topics that you might be interested in with respect to things like facial expression recognition, facial detections, a lot of the kind of the nuts and bolts, provides nice, good chapters describing some of the technical challenges that exist within a lot of these areas. But what's interesting about this encyclopedia is that in one of the chapters in the 2009 version, they essentially cataloged all the face databases that could be used for training and evaluation within this space. And so I'm not going to go through all these data sets, but I'm going to give you a minute to look at the representative images in the far column and ask yourself, which types of people are missing from these data sets? It's not going to take a genius to figure out the certain race and ethnic and gender classes that are being excluded from these original data sets that were used to train facial recognition technology. And the reason why that's problematic for performance is because if certain types of individuals do not exist within the database, then it makes it difficult for those algorithms to be effective in isolating or identifying those individuals for whatever task that you may have. And so the reason, so for research purposes, we could do things like validate our measures, et cetera, which I'll talk about at the end. But for applications like in policing, for example, that's a really bad problem because it means that the information that we're using to train the algorithm is biased because there's a massive selection effect in terms of the images that algorithm is going to be seeing. So this original paragraph that I kind of alluded to from Axon was from an ethics board that they communed in 2019 to look at facial recognition in body cameras. That board ultimately concluded that Axon should remove that technology or no longer pursue that technology, and Axon agreed. But at the bottom of this paragraph, there's this nice little footnote, footnote number 6. And so if you're to read footnote number 6, essentially what it says is a possible exception to the failure of facial recognition technology in this setting might be comparing the face of someone being booked to a pre-existing mugshot database. So the reason why I highlight this is because this gets back to facial verification versus facial identification. Facial identification is the system that is inherently plagued with just the inherent problem of not having enough training data, et cetera, because in those systems, again, you're trying to say, is this photo one of a million photos? Facial verification, which is what the mugshot database reference is in the Axon paragraph, is a much easier problem because the question that you're asking the machine you're not asking, is this person John Doe? You're saying, here's 2 images. Are these images of the same person? Which means that you don't need to know whether or not this individual is John Doe, Jane Doe, or whatever. You're just trying to say whether or not these 2 things are the same. So the reason why I'm emphasizing this point a lot is the contribution that myself and one of my students, Hang Ko, are trying to make to this literature. It's talking about how we can actually use that insight in terms of facial verification being effective in terms of facial recognition to improve the accuracy of these measures, and especially within small samples. So in our paper, we're mostly focusing on how do you develop facial recognition tools for underrepresented groups. So what's interesting about the progress of this manuscript is that when we first started the projects, we were thinking about members of Congress. So how do we identify small, a member of Congress who's maybe doesn't get a lot of press? How do we identify that individual on footage from a channel like C-SPAN? And so what we later found out is that the algorithm that we developed for that problem actually has a broader utility that gets at the heart of some of the problems that we have already discussed with respect to algorithmic bias. So first, let's talk about the member of Congress example. So some faces are easier to recognize than others. So Leonardo DiCaprio, Donald Trump, precisely because there's just so many images of that individual, so many data sets that includes that individual. It's much, much easier to identify that individual from a broader corpus. Again, we don't have to be talking about Leonardo DiCaprio or Donald Trump to understand the contribution, because we can also just talk about white men, for example, which is overrepresented in the data sets that we talked about in terms of facial recognition selection bias. The same story applies. So for this project, we collected closed captioning data and thumbnails, images from the Internet Archive. We used keywords related to women as a group, which I've used in previous projects. And then we looked at CNN and Fox News broadcasts. Specifically, we found 400,000 image text segments from CNN and 358,000 from Fox News. So ultimately what we used is called a Siamese neural network. It's also called contrastive learning in the literature. And so what this architecture does with respect to machine learning and facial recognition is that you give it two inputs, not just a single image, you give it two images and you say, okay, are these two images the same person? Yes or no, 1 or 0. So the reason why this model is really easy to train is because there's lots of data sets, mostly of celebrities, in which there's buckets and buckets of folders that say, here's a ton of images that are Leonardo DiCaprio, and here's a ton of images that are Donald Trump. So in that setting, what the algorithm is learning is not to say, what does Leonardo DiCaprio look like? But when I compare image A to image B, or input 1 to input 2, are these the same person? Which means that we can use a biased database, i.e. a celebrity database, to actually learn key properties that images have with respect to that specific task, and then use it for a specific purpose, i.e. in our instance, trying to identify members of Congress. So ultimately what we provide the algorithm is a positive pair. So we see Kamala Harris as a positive pair, two images that are the same person, and then two images that are not the same person. So Kamala Harris and Nancy Pelosi in this example. And then ultimately, those two pairs can be used to then train a model that will allow us to differentiate across a variety of members of Congress within footage from the Internet Archive and elsewhere. So let me talk a little bit more about the steps in this process. So we use the Google Vision API to extract faces from the Internet Archive. So we did face detection. We used the Google API then to determine the orientation of the face. So we took the estimated tilt, et cetera, from the Vision API. And then we paired every Internet Archive photo with a random selector of 500 celebrities who have most similar face orientation. So what this means is that for every image that we obtained from CNN footage, we said, okay, where are the faces in this image, in this frame? We took that face and then we compared that face to 500 randomly selected celebrities from a massive celebrity database of tens of thousands of celebrities. And then we tried to choose faces that had the same facial orientation. So we did the face alignment task, which I've already talked about earlier in the talk. And then once we had those pairs, we then used the algorithm I just talked about and scored those photos in terms of the likelihood that those individuals are the same person. And then what that would give us is a confidence interval that would say, okay, for a given Internet Archive photo, what is the realm of possibilities when it comes to selecting 500 random photos And that gives us some sort of error around that Internet Archive photo. And then we can use that and also a similar calculation done with the Internet Archive and a given member of Congress. And we can simply say, if the pair of a member of Congress and the Internet Archive is outside of this confidence interval, then we have a good sense that that pair is that member of Congress, i.e. a match has ultimately been found. So this is what the output looks like from our model. So we have two images on the left from Nancy Pelosi, where true equals 1, the prediction's really, really low. And then we have Nancy Pelosi and Emma Watson. Certainly not 0 because the head orientation is similar in these photos, but certainly greater than what we had for the Nancy Pelosi matches. So the reason why this, I think, is a promising approach to dealing with things that we know with respect to selection bias is because in this model, again, we're not trying to say that where is Nancy Pelosi in this haystack? All we're trying to learn from the model is that these two images are not the same person, which means that that's a much simpler problem. And it's also a problem where we have a known error rate, which we could use to our advantage when deciding between one face versus another. So ultimately, the substantive results that we had in our paper is that we found that female legislators appear on CNN significantly more than we would expect in Congress when women are referenced. And so this is based on the number of women that appear in the R data set versus the number of women in Congress who use the simpler language. That finding is what we should expect, hopefully. But we ultimately also found that when women appear on CNN, they tend to appear by themselves. And we ultimately found that when they appear by themselves, it changes the way that they talk about women as a group. And so I'm not going to go into the language model that they use, but it was a version of BERT, where we essentially looked at the way women were framed in those discussions. And when women were appearing by themselves, they used words like terrified, forgotten, horrible to describe women. When they appeared with men, they used Trump, anxious, Republicans, reporters. And then when they appeared with other female members of Congress, they used forgotten, awful, victims, horrible, which goes back to the similar types of language. So all of this is to say that not only can we identify female members of Congress on CNN, but when they appeal by themselves versus male colleagues or female colleagues, it fundamentally changes the way that they talk about women as a group. But like I said, I think that the approach that we're getting at in this paper, I think has broader applications that we're looking to exploring over the next couple of months, as explaining how this algorithmic approach can be used to resolve problems related to selection bias with respect to facial recognition. So Gender Shades is a very, very famous paper that deals with algorithmic bias. It's so famous that, in fact, they made a Netflix documentary called Coded Bias, which is drawing on this work and others, talking about algorithmic bias and how it implicates facial recognition technology. And so the reason why this is the image that is used for the Netflix documentary is because the author of the original Gender Shaded paper explained that when she was using the Google Vision API, for example, that oftentimes the only way that she could get accurate results with respect to her face was when she wore a white mask over her black skin, which is ultimately motivating a larger discussion about the effectiveness of that technology for certain groups. So the concluding paragraph of this paper, I think, provides a nice blueprint for where we can go as researchers in political science as we use this, or in the social sciences as we use this technology. So the first thing that they explain in the paper is that we need more inclusive benchmark data sets and we need to have subgroup accuracy reports. So I don't think that political scientists necessarily have the means to produce inclusive benchmark data sets, even though I do think that that is a worthy objective and that we should certainly try to pursue it at all costs. But I certainly believe that we can do the latter, which is producing subgroup accuracy reports when we present facial recognition technology that we want to use in our papers. So it's not enough just to say that our algorithm is accurate, but we need to say that it's accurate with respect to certain groups that we know that these algorithms have historically underperformed with. Secondly, we need to increase transparency and accountability within the artificial intelligence literature. So this is where I think Google and Microsoft can be applauded with respect to the Vision API and both of their platforms. The level of documentation and the level of warnings that they provide to users has expanded exponentially over the last couple of years, really highlighting some of the problems that they know exist within this technology and trying to make people informed consumers. And I think we definitely need to have a similar trajectory when it comes to our own work. These authors define transparency as providing information on the demographic and phenotypic composition of training and benchmark data sets. This is something we can absolutely do when we train our own algorithms for the purposes of our own research. We can talk about the demographic composition of our data sets. In some instances, we can't control the demographic composition, i.e. if we're training an algorithm to classify members of Congress, but it's certainly something that we should make readers aware of. And then finally, they define accountability as reporting algorithm performance on demographic and phenotypic subgroups and actively working to close performance gaps whenever they arise. So this again comes back to transparency with respect to showing how facial recognition performs across various subgroups. And then when there is subgroup differences, trying our best as researchers and try to close that gap for the purposes of for our own research question. So this overview hopefully has provided enough background with respect to facial recognition technology so you can begin to theorize about how you could potentially use this for your own work. Again, feel free to contact me either via email or on Twitter, and I'd be happy to share anything that I discuss with you as you develop your own projects, and happy to talk a little bit more about your specific research problems that where you think facial recognition could potentially become handy. So with that, I'm going to stop sharing my screen and I will open up the floor to any questions that you may have. Thanks. All right. So I think I'm also controlling the questions. So right. So sure, I will do Stacy, and then I think Patrick also has a question. So Stacy, go ahead.
I'm just wondering, I'm wondering about the use of this with databases that are archival, to the extent to which, because we had an exchange before the today's workshop about my use of these technologies for doing history. And I'm also just wondering if anyone has done any research on facial expressions and change over time. That is, like, is happiness or anger, you know, the way people present themselves in pictures, if that's changed over the past 100 or so years.
So to your first question, so in the chat, I'm going to post a link to the Google Vision API demo. So this would allow you just to drag and drop a photo into their API. And so the first question is, if you're using archival footage, are you getting the bounding boxes around the face of the individual that you care about? If you are, then you're heading in the right direction. If you're not, there's not going to be a ton that you can do in order to correct that problem beyond just having higher resolution photos. Now, with that said, you can think about, in terms of archival footage, if you're looking for a specific person, you know, that's going to be a harder problem than trying to classify a whole scene within a photo. So, like, if you're trying to say, is this a group shot? Is this an individual shot? Is this photo taken in a park? Those sorts of things are going to be much easier to deal with than trying to identify specific problems. But that's your first step. So in terms of facial expressions over time, absolutely. I don't think anybody's done this, but I think that it's certainly an interesting question in terms of how these things change over time. So in computer vision, age is often treated as a nuisance parameter. So we want our facial recognition technology to work across different age groups and as somebody ages. But I think as social scientists, we can actually think about how we can use that for inference purposes or research questions that we actually want to try to harness that change over time. And I think that that's certainly, not only is that an interesting question, but I certainly would imagine that it would exist because of what we know in terms of display rules with respect to emotions. So both of those are good. Cool.
Can I just follow up with a quick, sure, kind of newbie question? This Google Cloud Vision thing, can I just download that and then like set that up so that it will put a box around pictures?
So the link that I sent you, you can take a photo on your computer and literally just drag and drop it into this software. The output that you're getting from that drag and drop step is what you would get from the automated interface. So if you find that it gives you reasonable results over a couple of your images, then you could send me an email and say, hey, it's giving me reasonable results over the couple of the images. And then I could share you the code that I use on my own work to automate that process. So that's the reason why a lot of people use this tool, because it has this nice interface that gives you a sense of whether or not it would actually work for your type of images before you go through all the effort to automate it.
Thank you.
Patrick, you're up. Thank you for attending.
Thank you.
As you see, you're featured in several points. So.
Well, I appreciate that. It's always exciting to watch your work, and hopefully I'll be seeing you this upcoming week. Are you going to the Midwest?
I will not be, unfortunately, but next year.
Okay, great. Well, I've got a couple questions and maybe an answer of sorts to Stacy. As far as the facial expressions over years, of course, I think there's some terminology issues that I deal with. I think the first question is Google Vision, the API, they're moving towards more granular approaches where they can get with the action units?
I think they're moving in the opposite direction. It's my understanding that all of the emotion recognition section of the API is going to be removed by June 1st. And so I don't know what it's going to look like, in the next couple of months. And that's definitely concern. It's definitely problematic. And the reason why is because I think the academic community, like yourself and others who are interested in this, can use this appropriately because they understand the limitations of this technology. But the issue is that they've had like app developers who use it under the hood of whatever app that they're selling or whatnot. And that's not being disclosed to the public, which is getting into trouble because of things like algorithmic bias.
Yeah, I agree with you. It's you'll be presenting on that. I think latent bias is what you're talking about, which is emotion is something that's constructed. It's almost a cultural aspect to that in a lot of different ways, which is maybe why you couldn't get an anger face recognized effectively.
Yeah.
And
it was actually surprisingly challenging. I was like, this is concerning, because I was like, dude, this would work. And I was like, oh wow, it's not working at all. And I'm feeding it really high resolution photos because it's being taken on my iMac. And so it's like, I can only imagine. But it certainly did really good at smile detection, it seems. So
well, I'll send you a presentation I have, which will show you as far as what Nolda's face reader does. Second question is, and it built off of what Stacy was talking about earlier, which is face verification with an aging population. Have you looked with your study? I think it was Nancy Pelosi. And I believe you presented this earlier, correct?
I presented versions of this, yeah, like a little bit here and a little bit there, yeah.
Okay, which had fascinated me all the way through. Have you looked at Nancy Pelosi over her lifespan?
Maybe. It should work. Like really, the reason why I'm excited about returning to this project is precisely because like as I've read more of the algorithmic bias literature and the problems with facial recognition in that setting, is that I feel as though our approach should be resistant to a lot of that. And so I'm excited to try to explore that a little bit more. Generally speaking, it should be able to handle Nancy Pelosi as she ages, but I'm curious to see what that would look like in practice.
Okay, and if I may jump in with Stacy and maybe makes a couple suggestions. First
Sure.
of all, incredibly good question. That's something I'm looking at within a time frame from the 90s to 2020 as far as change within a small community, because there are display rules, as Bryce is talking about, that does influence how people show happiness. So it's looking at yearbook photos. But there was a study, which I'll see if I can track it down, was looking at paintings over a period of time. And I believe they coded the paintings going way back and found that there is continuity, certainly with smiles, although there are different types of smiles out there, which is why having different action units is very important, because these different smiles lead to different behaviors in the interaction with others. So I'll try to look that down. You're located at at Purdue, yes. Okay.
Yeah.
Okay. So great questions, and Yeah, definitely. And thank you for this presentation. Awesome stuff. And I'll send you an email with some other questions.
Excellent. Okay, we're at 3:30, which is the end of our scheduled time. Is there any last minute questions that people have? As they're formulating that last minute questions, I would like to reiterate that in the next couple of weeks, we're going to be sending out an email survey to the past participants in the workshop series, get some feedback on the format. So like I said, today we did more of kind of this broad, overview of a research area and less of like a tailored research presentation on a specific paper. The previous two talks that we had were more specific research presentations. And so we're interested to get feedback on that format to see which is the preference for folks. And then we'll be asking some other questions as we improve the video workshop series for the fall. So that's it. The video workshop series is done for the spring semester. We will continue again in the fall. Look forward to seeing everybody there. And please follow our Twitter feed or go to the CCSE website to provide other information on other things that we're doing over the next couple of months. So take care.